The universe is vast. It is ancient. For all of human history, it has been overwhelmingly silent. We have gazed at pinpricks of light in the night sky, wondering, dreaming, asking, are we alone? We shouted into the cosmic ocean, only echoes returned. That is, until now. A new eye opened. It peers deeper into darkness than ever before. The James Webb Space Telescope, a golden honeycomb adrift in the void. It has captured something extraordinary. It intercepted a whisper from a world impossibly far away. A faint message on a beam of starlight traveling for over a century to reach us. This isn't a radio signal. This isn't a fleet of starships. It's far more subtle, far more profound. A chemical fingerprint, a ghost in the machine of a distant planet's atmosphere. To understand what the James Webb Space Telescope has found, you must first understand what it is. It is not merely a telescope, it is a time machine. Light, the fastest thing in the universe, still takes time to travel. The light from our sun takes 8 minutes to reach Earth. When we look at the Andromeda galaxy, we are seeing it as it was 2.5 million years ago. We are always looking into the past. Webb is designed to look deeper into that past than any instrument before it. The universe expanded and stretched the light from the earliest stars. That light shifted from visible into infrared, its massive 6.5-meter primary mirror, 18 gold-coated beryllium hexagons, so sensitive it could detect the heat of a bumblebee on the moon. That sensitivity lets Webb pierce cosmic dust, gas, stellar nurseries. By gathering infrared light, Webb unlocks a hidden universe. So, how does Webb actually do it? How does it analyze the air of a planet over a quadrillion kilometers away? It's called transit spectroscopy. We wait for a planet in its distant orbit to pass in front of its host star from our point of view. As the planet crosses the face of its star, it blocks a tiny fraction of the starlight. During the transit, a tiny sliver of starlight filters through the planet's atmosphere, if it has one. The journey through this alien air changes the starlight. Different molecules in the atmosphere absorb specific wavelengths: water vapor, methane, carbon dioxide. Each molecule has a unique absorption signature, like a chemical barcode. Webb's instruments capture this altered starlight and spread it into a spectrum, a rainbow. The spectrum is riddled with dark lines like missing notes in a musical scale. By mapping these lines, scientists identify which molecules are present. It is cosmic detective work of the highest order. Our story now takes us to a specific point of light in the constellation Leo. It is a faint red dwarf star named K218, located about 120 light-years from Earth. Orbiting this dim, cool star is a planet called K218b. This is where Webb has been staring. K218b is not like any planet in our solar system. It's what astronomers call a sub-Neptune or a Hycean world. It is about 8.6 times more massive than Earth and about 2.6 times wider. K218b is special because it orbits within its star's habitable zone. This is the Goldilocks region, not too hot, not too cold, where the temperature could be just right for liquid water. And previous observations from the Hubble Space Telescope had already given us a tantalizing hint: the unmistakable signature of water vapor in its atmosphere. The ingredients were all there. Scientists couldn't wait to point the telescope at this world and see what other secrets its atmosphere held. So, the mysterious molecule was dimethyl sulfide, or DMS. On Earth, DMS is actually a compound most people haven't heard of, but they've almost certainly smelled it. It's a major contributor to that familiar smell of the sea. DMS is produced almost entirely by life, specifically phytoplankton, tiny marine algae floating in our oceans. For astrobiologists, DMS is a biosignature. It's a chemical fingerprint tied to biology, and its presence in an alien atmosphere is hard to explain abiotically. Finding a potential DMS signature in K218b's atmosphere electrified scientists. It was the first tentative detection of such a life-linked molecule on a habitable zone exoplanet. This was different. A molecule that shouldn't persist without life replenishing it. It was, you might say, a whisper: something is alive here. Feels like science fiction, but it's meticulous, patient science. The signal is weak, on the edge of detection, so scientists use careful language: potential detection, evidence suggests. The reason the potential detection of dimethyl sulfide is so compelling goes beyond its biological origin. It points to a concept crucial in the search for life: a planetary atmosphere in a state of disequilibrium. Mars is a good example. Its thin, carbon dioxide-rich atmosphere is largely in chemical equilibrium, geologically dead, chemically dead. Life, on the other hand, is a force of chaos. It constantly pumps reactive gases into the atmosphere, creating a chemical cocktail that really should not exist. Earth's atmosphere is filled with oxygen. Without the constant work of plants and photosynthetic bacteria, that oxygen would react with rocks and minerals and disappear from our air. The simultaneous presence of oxygen and methane is a massive chemical imbalance, a screaming signal of disequilibrium. The potential presence of DMS on K218b with methane and carbon dioxide hints at exactly this kind of disequilibrium, a source that looks a lot like a global biosphere. While the headlines may scream, "Alien life found," scientists remain measured. This is the nature of science. Extraordinary claims require extraordinary evidence. The research team itself has emphasized that the detection of dimethyl sulfide is tentative. The signal is weak, buried in noisy telescope data. Could unknown non-biological chemistry produce DMS here? Could the physics of such a massive atmosphere create signatures that mimic DMS? These are questions scientists must now work tirelessly to answer. The next step is verification. This involves repeated observations of the target, getting more data to improve the signal-to-noise ratio. It also involves peer review, where other experts scrutinize the methods, analyze the data, and challenge the conclusions. This rigorous process separates discovery from speculation. So, while the world holds its breath, the researchers are rolling up their sleeves. They understand the weight of what they might be on the verge of discovering. So what happens next? The discovery on K218b is not an end, but a beginning. Beyond K218b, the search will widen. One world among thousands of known exoplanets. Webb is just getting started. Scientists now have a new target molecule to hunt. Point JWST at promising Hycean worlds, planets in habitable zones. Find it on multiple worlds, and the case for biology strengthens. Multiple detections across star systems become a pattern. The search will expand beyond just DMS. Scientists are building a library of chemical fingerprints: oxygen, ozone, methane, more exotic molecules from unfamiliar life. The goal: a comprehensive chemical census of nearby atmospheres, from single molecules to full atmospheric systems. Learn their weather, their clouds, their potential for hosting life. This data will revolutionize planet formation theories, a new era of comparative planetology. The next decade promises the most exciting era in the history of astronomy. We stand at a remarkable moment in human history. For millennia, the question, "Are we alone?" belonged to philosophers and poets. Today it's an empirical question. We have the tools and the ingenuity to answer. The James Webb Space Telescope is more than hardware. It's the physical embodiment of our species' deepest curiosity. It is the extension of our senses, reaching across unimaginable gulfs of space and time to touch the air of another world. Whether this particular signal is life or not is, in some sense, secondary. The journey itself is the prize. That we can ask these questions and build machines to seek answers is a testament to human intellect and drive. Each new piece of data, each new spectrum analyzed, adds to the grand mosaic of cosmic knowledge. We are learning the universe is stranger, more wonderful, and more complex than we imagined. Imagine a future with a catalog of nearby worlds, some with atmospheres rich in oxygen, others shrouded in methane, and a few, like K218b, whispering of a marine biosphere. Imagine knowing with scientific certainty that stars warm other living worlds, a future where humanity sees itself as part of a vast, interconnected cosmic web of life. The quest continues. The silence of the void has been broken by a whisper. Now we listen more intently than ever, our new golden ear turned to the stars. Look up at the night sky, the universe is waiting.